Hello and welcome. Why do chicken coops have two doors? Because if they had four, it would be a chicken sedan. In this video, we're going to learn the comparison tests for series. Let's check it out. So you remember the comparison test for integrals? That was back in 7.8 when we were learning about improper integrals and whether or not they converge or diverge. Well, it turns out that series have a similar test to determine convergence and divergence. But before we go into that, it's going to be helpful to have a bunch of series that we can compare things to. And before we even do that, it's helpful to know what kinds of expressions grow faster than others. So in this first line here, the n to the n is going to grow much faster than n factorial. So this little greater than symbol, you can read grows much faster than n factorial, or is just a lot bigger than n factorial when n is large. And so this is going to order for us the kinds of expressions that grow faster when n gets large, and the ones that grow more slowly when n gets large. So n to the n is growing the fastest out of all of these, followed by n factorial, followed by the exponential functions, so like 3 to the n, 2 to the n, exponential functions that have a base that's bigger than 1, followed by the n to the power of kind of functions like polynomials, so n raised to some number power, so n squared, even n to the 1.1. Here's n to the first, here's the square root of n, the cube root of n. Each of these are growing more and more slowly as n approaches infinity, so like n squared would grow faster than n to the 1.1, and n to the 1.1 would grow much faster than n. The cube root of n would grow even more slowly. And then last of all on the list is ln n, which grows exponentially slowly. So as n increases, ln n is not increasing that much. Now if you flip all of these, which is mostly the way we're going to be looking at them in terms of series, because the terms of the series have to shrink down to 0, and these things are not shrinking down to 0, they're blowing up to infinity. But if we flip all of them, so write 1 over n to the n, 1 over n factorial, and so on, then what we've got is the reverse situation. 1 over n to the n grows a lot more slowly than 1 over n factorial. And 1 over n factorial grows a lot, or shrinks a lot more slowly, I should say, or is a lot smaller than 1 over 3 to the n. Actually, each of these are shrinking as n goes to infinity, so I probably misspoke there. But basically, these things on the left are a lot smaller than the things on the right in this row. So some of these things we can look at as being our familiar kinds of series. For example, all of these guys are p-series. These are p-series. And by the way, I'm writing these without the summation in front of them, but if these were stuck inside of a summation symbol, then it would be a p-series. Here p would equal 2, here p would equal 1.1, here p would equal 1 and a half and a third. So all of these are under the category of p-series. Over to the left of the p-series are geometric series, like 1 over 3 to the n and 1 over 2 to the n. So these would be convergent geometric series because the common ratio would be 1/3 for the 1 over 3 to the n. That would be a 1/3 common ratio, the r value in other words. The 1 over 2 to the n would be a half for the r value, which would also converge. So these are convergent geometric series. And for the p-series, they converge when p is greater than 1. So that would be the 1 over n squared, the 1 over n to the 1.1, those kind of series. and it would diverge when p is less than or equal to 1. So that would include the 1 over n, the 1 over square root of n, and so on. By the way, each of these have another series in between. Like there's a 1 over n to the 0.9, for example, that would be in between the 1 over n and the 1 over square root of n. But these are some of the common ones that you might see. But the main thing is, at some point along the line, it goes from a convergent series to a divergent series. And this is really the place where it happens, is right here. 1 over n is like the boundary, more or less, between, well, at least of this list, between the convergent and divergent kinds of series. Divergent to the right, and convergent to the left. Again, we're talking about series, so each of these would have a little summation symbol in front of them, right? Little summation symbol. So with the summation symbols, you get convergence over here to the left, and then with the summation symbols, you would get divergence over to the right. For example, the sum 1 over n, we know that diverges. We've proven that in a previous section. Now, these ones I just kind of told you that n to the n grows faster than n factorial, but how could we show that kind of a thing? For example, how could we show that 2 to the n is growing much faster than n to the third? So that it's much bigger than n to the third when n is large. Well, limits and L'Hopital. What we can do is compare the two using a ratio. So find the limit as n approaches infinity of 2 to the n over n to the third. And if you get infinity, that means 2 to the n is growing faster than n to the third. These numbers on top are getting bigger faster than the numbers on the bottom. And that's what we get here. So here, this is like an infinity over infinity, so we can use L'Hopital to take another step. We would take the derivative at the top, which is 2 to the n ln2, and then the derivative at the bottom, which is 3n squared. By the way, here we're treating n as a continuous real valued function, or a real valued variable, and taking the derivatives on top and bottom, just in n. Then we get an infinity over infinity again, so we take L'Hopital again, take derivatives of top and bottom. Another ln2 pops out by the derivative of 2 to the n. Once again, infinity over infinity, do another L'Hopital. So this is 2 to the n times ln2 to the third. That 2 to the n is just not going away, whereas these derivatives are eating away at the polynomial on the bottom. And now at this point we just have 6. So the top is blowing up to infinity, the bottom is staying at 6. So overall, the fraction is blowing up to positive infinity. So this would show that 2 to the n is growing a lot faster than n to the third, at least when n gets larger and larger and larger. At the beginning, it might not be bigger. Like if you plug in n equals 2, you get 2 squared, which is 4, and then 2 to the third, which is 8 on the bottom. But 2 to the 100 is much, 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 much bigger than 100 to the third. So eventually, the 2 to the n wins out. So you could do that with any pair of these. Take the limit as n approaches infinity of, say, 3 to the n over n factorial. In fact, when we talked about looking at sequences in 11.1, we did that kind of a thing. We proved a couple of these that have like an n to the n, comparing that to n factorial. We compared n factorial with 3 to the n. So we kind of showed some of these parts already in 11.1, the notes. Okay, so when we have these comparisons, we're able to say something about whether or not a series converges or diverges based on where it falls along this spectrum. Now, what we can do, and so if we know, for example, that all of these as series converge, then it gives us a whole set of series that we can compare other series to using the comparison test. So the comparison test for series works almost identically to the comparison test for integrals. And it's not too surprising because in the last section we were making that strong connection between the improper integrals and series, saying that if the integral converges, then the corresponding or related series would have to converge as well. And similarly, if the integral diverges, then the series has to diverge as well. So we've made that connection with the integral test. So it makes sense that the comparison test would work very similarly. So here we have, suppose a sub n and b sub n have non-negative terms. We need that non-negativeness for this comparison to work. And big N is some integer, so this is like far enough, this is representing far enough out there in the series. Then if a sub n is less than or equal to b sub n, and here it's kind of helpful to have a tie as to what a sub n and b sub n are supposed to be representing when you're working on examples. So I'll just mention that here. A sub n is supposed to be representing the series that you want to find something out about. So this is representing an unknown. We don't know if this converges or diverges. This is the series that will be handed. We'll be given this series. So this is given. The b sub n series is going to be the one, and actually I'm going to highlight this in red because we're going to use red to represent the b sub n's in our examples. So the b sub n series is representing some known series. It's going to be one of these series up here that either converges or diverges. So this is going to be something that's known. Okay, so if we have our series, if the terms of our series are less than or equal to the terms of the known series that we're comparing to, and if the known series converges, then the smaller, see these terms are smaller, the smaller a sub n series also has to converge because its terms are smaller than the b sub n's. And so it's going to converge to some number that's probably smaller. So then if the reverse is true, so if the b sub n's are smaller than the a sub n's, here, so basically here it's like the a sub n's are bigger, then if the b sub n's as a series diverge, then the bigger a sub n series also has to diverge because they're bigger, and they're going to add up to a bigger infinity, you can think. So very similar to the comparison test for integrals. Let's see these comparison tests, or this comparison test in action. Here we have a series. These are the a sub n's here. You can think if you want to compare them, that was a bad pun. If you want to tie them to the comparison test. So this is like your a sub n series. And we want to figure out, does this converge or diverge? Well, let's look at its terms and see if we can compare them to the terms of a known series. And here what we're going to do is just strip away all of the terms on the top and the bottom that are not the leading terms. We want to just reduce things down into the leading terms, the ones that get bigger faster as n approaches infinity than all the rest of the terms on that side of the fraction. So for example here, the leading term on the top is just 5. There's only one term on the top. On the bottom we've got 5n. And if we go from the left fraction to the right fraction, what we're doing is we're increasing the size of the denominator, which means that the fraction on the right will be smaller. Right? When the denominator of the fraction increases in size, that makes the overall fraction smaller. But this one will simplify down to just 1 over n. I'm just going to put a little note here that this inequality is true for n greater than or equal to 1. As it mentions, you want to have some big N, some point in the series where after that this inequality is true. And if you can't have that, then the argument doesn't really work anymore. So this is just saying eventually the terms of this series that we were given are going to be bigger than the terms of the series 1 over n. And then we'll finish off here by saying since the series 1 over n diverges, and we can give as a reason it's either the harmonic series or because it's a p series with p equals 1. Harmonic series was just a name for that sum of 1 over n. So since that series converges and the terms of our series are even bigger, well then our series is going to converge too because it's got some bigger terms. Yep. So this one also diverges. And you could just say by comparison or by the comparison test. If it's asking for a given name of a test, you could just say comparison test. Okay, so that shows that this series right here diverges because we can compare it to this other known series that diverges. And we have to make sure the inequality direction is working in the right direction, just like with the integral test. Let's check out example 2. So here we have the sum as n goes from 4 to infinity. Now we've got to write the n equals 4 to infinity because no longer can we get away with this shorthand notation that assumes n starts at 1 and goes to infinity. But that's okay. Good practice writing. So what we'll do is we'll take the stuff inside, we'll take the terms of this series. And by the way, this is a square. This is n squared. This is not like an index of 2. Sometimes it's a little hard to tell, but usually if we wouldn't write an index of 2 anyway, so that's one of the giveaways. Well, let's look at the leading term of the top, the leading term of the bottom, which is that n squared square root of n. And here, if we look at what happens from this fraction to the next, we're adding something to the top, which would make this fraction bigger. And we're also subtracting from the bottom. If we're subtracting from the bottom, that makes the overall fraction bigger as well. So moving from the left fraction to the right fraction, this new fraction on the right is going to be bigger than the old fraction, both because we're adding to the top of the fraction and subtracting from the bottom of the fraction. Now, if we had to like add to the top and the bottom, well then it's hard to know if that new fraction is bigger or smaller than the old fraction because things are happening both to the numerator and denominator that are competing against each other. One of them's making it bigger, one of them's making it smaller. But in this case, both changes that happen to the top and the bottom are both moving the fraction to be bigger than it was before. Now we can simplify. So we'll have like an n cancels. And it's helpful to write this as 1 over n to a power. This is n to the first times n to the 1/2, which is n to the 3/2. And those are the terms of a known series. That's a p-series. We know when that converges and diverges. So as I'm writing this, what does it do? Whoops. Does the series 1 over 3/2 converge, or does it diverge? If you said converges, that's correct. This is a p-series with p equals 3/2, which is, I guess I'll put in here, 3/2 is greater than 1, and that's what makes it converge. So since that known series converges, our smaller series has to converge as well. There we go. Sometimes this is called the direct comparison test because you're directly comparing the terms of one series to the terms of another series through this inequality. Let's check out one more example. So example 3 says, does the sum n equals 1 to infinity of 1 over 2 to the n plus 1 converge or diverge? So once again, we're going to write 1 over 2 to the n plus 1. Oh, actually, before we move on, I want to say one more thing about example 2. This inequality is true for n greater than or equal to 4. I mean, when you add something to the top of the fraction and you subtract from the bottom of the fraction, that's going to make the fraction bigger, assuming you started out with positive numbers on top and bottom. But then we have to have the terms of this series non-negative. So that means positive or equal to 0. And that's true when n equals 4 or greater. The top and the bottom are both non-negative. All right, so just wanted to point that out. And so here we're going to look at comparing this to 1 over the leading term of the bottom, which is 2 to the n. Here we're subtracting from the bottom. If you make the bottom smaller, that's going to make the overall fraction bigger. And in fact, that's pretty much what you're comparing it to. I'm going to write it in one more step. I'm going to write the form a little bit different. 1/2 to the n. That way you can see it as a geometric series. And you can see what the r value would be of that geometric series. And this inequality is true for n greater than or equal to 1, which is all we need for this series. So since the series, and I don't have to write the n equals 1 to infinity, I probably should choose the right color. Since the series 1/2 to the n converges, hopefully you beat me to that, because it's a geometric series with r equals 1/2. Remember, as long as the common ratio is between -1 and 1, then you're good to go. That geometric series converges. Otherwise, the geometric series diverges. So since the series 1/2 to the n converges, then our smaller series is going to have to converge as well. Okay. Now what about the series 1 over 2 to the n minus 1? What if the inequality is just not going the right direction? What if this smaller series converges, but then our bigger series, does it converge or diverge? What can we do about cases like this? The answer is in the next video. Thanks for watching, and see you in the next video.